Welcome. Today we will be presenting to you our collaborative project with the Mechanical Engineering and Civil Engineering Department's Solar Tree Project. My name is Eric Foodie.
I'm Justin Harrington.
I'm Manav Gujrat.
So, to begin with the introduction, I don't know if you want to.
So let me begin by first explaining what a solar tree is. A solar tree is actually a structure which is designed to mimic a real tree, but instead of actual leaves, it has solar panels to harvest the sun's energy. And this power can be used to charge electronic devices of all sorts, like phones, tablets, electric scooters. And it's really the purpose or the intent for it is to be free for the public and to be in places like parks and schools. And in figure 1 you can see the first concept designed by the Israeli company Sologic. And as you know, that the solar market in the US is booming and has more than quadrupled in the past 5 years. So it's really, our belief is that the demand is very high and this is the right way to channel engineering efforts towards solar power.
So for our proposed design, we use the angles of the sun, which is this figure shown on the lower right, and that shows the angles of the sun throughout the year. Usually the sun is pointed towards the south, but however high or low depends on the time of year. So we wanted to we were inspired by the design that was shown on the previous slide with the different angles, but we wanted to keep consistent angles and just make it adjustable throughout the year using a hand crank, which we'll get into. Our final design is shown over here. Has a table and chairs to support.
Yeah, so the final design would have the moving crank mechanism, charging station, and solar panels. The main way that we wanted to get it to move, to position the panels, was a bevel gear and shafting system, which would be rotated by a mechanism. And the input to the crank would be from a human input user. About 130 newtons. 130 newtons we found was about what the human input would be able to get. We got that from a website called Engineering Toolbox that helped us come up with that estimate. The design of the top structure was one of the big aspects of the civil engineering part, and it definitely helped the mechanical engineers with designing the shafting and bevel gear system, and so working together with the departments that assisted us in creating a working and safe design.
So this is, of course, a concept that might be familiar to everyone at NJIT. These solar panel trees are already at NJIT's campus. This one over here is in front of Laurel Hall. That one's been there for a few years. And this one over here is in front of the campus center. There's actually multiple on campus. You can even see another one in the background. And both of these are fixed, but they do essentially the same thing that we're trying to accomplish, which is charge devices on the go. But unfortunately, there are some structural problems with these. This one, the top portion just completely blew off during a storm. And so we were working to address that and make it movable.
So for the procedures of this project, we boiled it down to a few main topics, mainly being the kinematics and the statics. So the mechanical engineers worked on the kinematic aspects, such as the gears and the shaft being moved by a crank, and civil engineer worked on the static aspects, such as the top solar structure and the foundation of the tree. This work was broken up individually between us. The choice of solar panel was another big aspect of it, as we wanted to have enough power to be supplied, and also the dimensions of the panel and the leaves of the tree were dictated by that, so we all worked together to research and look things up on solar panels. The team came up with 2 configurations. One, which was a lower wattage per panel but had 6 panels, and 2, which was a 400 watt per panel with only 3 panels. And after going over it a few times, configuration 2 was decided to be the best one, as it was less weight, less dimension sizing, and overall a better look for the tree. And so the gears is the first big element of this project that we're going to go over. The choice of bevel gears was simply due to usability and the fact that they're widely known, and also work well for the type of dimensions and angles that would be used for the shafts. The gears were all designed using AGMA requirements. The team found a nice module for AGMA bevel gear design from a Spots textbook, which is explained later but in the report. But this figure 8 is essentially what was used to design all of gearing, excuse me, all of the gear sets, the 2 gear sets. So using this, it made it much simpler. The dimensions of the gears shown here in this figure 7. The top set is the more important in terms of gearing because the main problem that was focused on is the power to overcome the moments that were felt at the top of the solar tree by the moments and forces of the solar structure that the civil engineers worked on. And so it was found and designed that 2420 inch-pound force, which was allowed to be output by the gears, was more than sufficient to overcome the power of the top solar structure, and therefore it could be rotated by a human input with a 1:4 gear ratio for the bottom and a 1:2.4 for the top set of gears. I believe, yeah. And here are some videos. The first 2 videos are the bottom gear set moving in the SolidWorks simulation, which shows that they mesh nicely and the design works out well, and the top gear set, which also meshes nicely and is nicely simulated here. And the final video that we can show is this is the mechanical engineering demonstration. There was a civil as well, but it just demonstrates the kinematic movement of the solar tree structure due to the gears. This is like a placeholder body, but the main aspect here is the top solar structure, the movements. And we also did, as a team, the stress plots and displacement plots of both gear sets. It was decided, and it was found out that through the use of ANSYS Workbench that the stresses and the displacements are all well below what is considered failure. The displacements were negligible, and the stresses were below the failure of the material chosen for the gears.
So now we'll explain a little bit about the shafting design. As you can imagine, there's a lot of force multiplication and a lot of rotating shafts here. So the loads on the shafts are primarily torsional and bending moments, although there is, for the central shaft, there is axial loading as well. So yeah, that's why the primary design for the shafts is to prevent fatigue failure because of the alternating loading that you can see in figure 1. So that's why our material choice was AISI 4041 hot rolled steel. It's a very common and cheap material used in all types of transmission shafting applications. And the design equations are primarily designed or derived from ASME standards for design of transmission shafting. And also maximum shear stress theory is applied in order to find dimensions for the shafts. And here in table 2 you can see a summary of the different shaft diameters that we found. For the input pinion, where the human would apply the force, it's a diameter of 0.5 inches with a factor of safety of 2. And the central support shaft is a little thicker because it has a lot of load bearing. It has 2 gears attached to it, so it has a little bit of higher factor of safety. And then the output shaft is 1.25 inches. So to validate the theoretically derived diameters, we also did some FEA analysis. On the left, you can see the top shaft is the displacement plot, and as you can see, the max displacement is almost negligible and impractical for the application. So, and on the right, you can see the bottom pinion shaft, the input shaft, and the displacement is even lesser, despite of the high torques involved.
So we designed the top structure, which is shown in a different slide, as having a square, a hexagon, and a leaf shape, all of which were made out of 1.5 inch pipes, which were welded together. And then these 2 construction details show how the top one shows how that structure will be attached to the rest of the structure, to the 4-inch of 6-inch pipe with bolts or screws, and then the bottom one shows how all those 6-inch pipes are welded together and then connected to the main shaft, which is a 12-inch pipe with bolts and a plate with a pin that rotates the entire thing. We analyzed this entire structure on SAP 2000, and we were able to determine moments and forces due to wind and weight. So here is shown the SAP 2000 models. One is the extruded version, that's obviously the one with the thick pipes. And then up at the top, there was the table of all the loads that we have analyzed. So then going down to the foundation, we chose a concrete footing, which is pretty typical. It's a 5.5 by 3.5, and then there's a steel base plate on top of that. The whole structure will be bolted down into the footing. The base plate is 1 inch thick, and it will support the entire structure.
So for the closing statements, just to go over everything that existed. As a team and as a project group, the joint work between civil engineering and mechanical engineering departments has been a good benefit for this project, especially this type of project with structures that must be static and also moving aspects, which need to work together well. Things shown, such as the loads and the wind loads, were all considered after they were created from the civil engineering side. The mechanical engineers took that and we worked together to make the gears work because of those loads, and the top structure was able to rotate because of that. And it was all able to happen because of the civil engineer and mechanical engineers working together with our different knowledge on these types of things. The core elements of the project, which is basically the top structure, the gearing system, and then the shafting system, right? And the workstation structure, I suppose. Yeah, so everything coming together, it was all, the main elements were satisfied and found, and so because of that, it has turned out very well, I believe, and so that's what we found.
Thank you.
And so, all right, I guess we get questions from Simon, I guess. There's no one else in here, but.
All right.
First one. This is the first one. I thought when I was coming in as a freshman that it was like this normally, but it is actually just all civil engineers in one group or all mechanical engineers in one group. This is what I thought it would be like.
Yeah.
So I'm glad I've been able to be part of this project because that was more to my expectations.
I've had a few capstone projects. We made a 40-story building in your class, as well as last semester we did a set of site plans, and then when I was getting my associate's degree at the County College of Morris, I was a mechanical engineering technology major, and I designed a new spike bench for track shoes because I was on the track team at the time. So that was also a capstone project. Yeah, but this one has really been like a full circle moment for me because I came in here as a freshman as a mechanical engineer, and that year I chose to switch to civil engineering and really start concentrating on that. But it's nice to kind of reconnect with the mechanical engineering side and kind of see what maybe I would have been doing and know that I'm very confident in my choice as a civil engineer and I prefer the work of civil engineering. Nevertheless, I enjoyed this project and interacting with these two and working with them. It's been great.
Yeah, it's been good.
For me, it was this was my first course-based capstone project. But apart from that, we can call it a capstone project. But I was the mechanical lead of the solar car team, so I designed a lot of mechanical systems for them. So yeah, that was like a project pretty much, where I had to work in a team, and we had to develop the mechanical systems like suspensions. The challenges that we encountered, I believe, it was like actually practically considering all aspects of it. Like when you design a gear system, you have to consider how will each decision impact other aspects, and whether you'll be able to, because we're designing it with in mind, keeping it in mind that manufacturability is one aspect that I think we learn later in our education that is the most important aspect for engineers.
Yeah, it was definitely a challenge. For us, it was a challenge doing the bevel gears especially because we don't actually learn that aspect in our previous classes. So teaching ourselves, first off, how to even do those was a challenge in itself. I did a lot of the gears and then Manav did a lot of the shafts. So attaching those to the shafts as well, I'm sure for him, was also a challenge because you have to consider all the forces that come in that are different from all the other types of gears. And then, as he said, how they apply, how they'll be manufactured, things like that. We had to consider material choice. We don't typically, a lot of the problems, like just classwork problems that you get in a textbook don't have you looking on the internet looking for material choice of like what's a normal gear made out of. So you have to think of these different things, and it's a fun type of challenge, I think, for this type of project.
It's a good exercise for the career.
Exactly.
So you're basically has more benefit and good feedback. You would like to recommend your next student for this type of capstone project?
I would absolutely recommend. The capstone project is the only. I had my friend tell me this. It's one of the few times you get to actually feel like an engineer while in school. Because you're actually designing it and doing everything yourself. You actually feel like you're an engineer working, So I think it's for that experience alone. And also, it's a lot of fun working with a group when you all know, what you're doing and stuff. So.
Yeah, because in a real world project, you always work with other engineers and other types of engineers. So it's like everyone has to know like a little bit of the other stream as well in their, whatever they do. So I believe that not only for mechanical and civil, it could be, across the whole engineering curriculum with electrical engineers and other types of engineering as well. That would be really beneficial. Yeah.
For me, this was one of the projects I was most passionate about, as I'm president of NJIT Green, and I just thought these would be a great addition. I'd seen the ones on campus. I wasn't totally pleased with how they just looked and kind of functioned. The one by Laurel barely charges the phone. But it's also something I was able to bring up on like almost every job interview that I had. I was able to just tell them a little bit about it, and if they asked to see anything from the project, I could just open the Miro board and kind of be like, this is where we have all of our ideas. It's kind of a mess right now, but we have lots going into this. And just being able to talk about that collaboration definitely gives you an edge because in the industry you're going to be working with different types of engineers and designers. So. It's definitely an interesting experience, and this was also something I raved about to my friends and family because I was really excited about the solar panel tree and what it could be.
That's good. Good. All right. Good job.
Pictures enough. I can't wait to hold up.
Okay, so I'm Erin Foodie. I'm graduating this semester, tomorrow actually, and I was on the track team within the sorority, and my favorite was heading the NJIT Green Club, which was a club for sustainability. I'll be going into civil engineering and working as a design engineer at a consulting firm, NV5, this summer. There I'll be an environmental engineer, and I hope to one day be able to make an impact environmentally through sustainability and sustainable designs. Pretty much. And then working on this project has been really awesome and kind of pushing me towards this goal with the solar panel tree aspect. Solar is a huge green energy sector right now. It's really being pushed by the administration. And so it's awesome to work on a project like this and even work with collaboration, mechanical engineers. You can introduce yourself.
So, hi everyone, my name is Manav Gujrati and I'm a mechanical engineer. I'm also graduating this semester and I'm very passionate about engineering and mathematics, especially applied mathematics. And my long-term goal is to pursue aerospace engineering and making aircrafts more efficient. But currently I'm an equipment design and engineering intern at NJ Transit. Going to be promoted to assistant engineer soon, as Aaron said, solar is a big growing industry right now, and even at the public transit level, New Jersey is buying a lot of battery electric buses, So just electrifying the whole grid is, or the whole system is the long-term goal. And NJIT has really helped me prepare for a long-term career and a flourishing career in terms of their hands-on learning experience and the classes that were very relevant, and it was a really good experience.
All right.
And I'm Justin Harrington, also mechanical engineer, also graduating tomorrow. I've been doing engineering here at NGT for 4 years now, and at the end, I think it's been a good time, at least. Just learning how to do different types of applications of all the things you learn, just thermodynamics, machine design, there's coding, there's all these different things, and they all culminate at the end and with this nice just group of knowledge that you end up with, and you can take it anywhere, especially with mechanical engineering. And in my eyes, you can take it pretty much anywhere: aerospace, medical, engines. You can do model those end-to-end transits like buses and trains. You can go toy, anything. And so I just think the broad applications of engineering, especially, is one of the main things that makes it shine and stand out to me, and that's why I've pursued it.